Hi-ho, we're still working on analyzing voltaic cells and figuring out their voltage generation and various other details about them. So let's see what they have for us now. There are two half cells in a voltaic cell. One is, I'm just going to sketch this as they describe it. Of course, there's a salt bridge between these two cups. And they say one of the half cells contains an iron electrode. So we have a chunk of solid iron in a solution of iron 2 sulfate. So in the liquid here we have iron 2 ions, and they probably won't matter, but we have sulfate ions as well. And on the other side we have a silver electrode in a solution of silver nitrate. Silver nitrate consists of silver ions and nitrate ions. And implicitly there is water in both of these containers, which again usually doesn't do anything, but it's good to keep it in mind. Every so often it'll surprise you and actually participate. So they want the cell potential, the oxidation half reaction, the reduction half reaction, and the overall cell reaction. The order in which they ask for these things is not a great order to approach them in. Typically, you're going to go to the redox table and find your SOA and your SRA first, and not only that, the order I wrote those in isn't the order you want. Because if you're the SOA, you're the thing that gets reduced, and if you're the SRA, you're the thing that gets oxidized, right? So let's find those things first. Our list is silver, silver ions, iron, iron ions, and then the ones that probably don't matter, sulfate, nitrate, and water. Let's see what the stars of our show are going to be today. We don't have that. We don't have lead. We don't have manganese or gold or perchlorate. La, 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 la. Here's nitrate, but they didn't say anything about acids. We do not have hydrogen ions, so this one can't happen to any important extent. Silver ions. These will be our strongest oxidizer, and so our SOA reaction will be silver ions gain an electron, turn into silver metal, and as you probably noticed, or you can look it up now, the potential for that half reaction is 0.80 volts. And now we go back and we're going to read up the right side looking for our strongest reducing agent. You can follow me doing that, or pause the video and see if you can find it yourself, and then see if we agree in a moment. Have any of these things. We have SO4 but not SO3, and we're not basic anyway, so that doesn't interest us. Nope, nope. We have silver metal, but we don't have sulfides, so this is irrelevant. Nope. Iron metal. The iron will be our strongest reducer. And so, iron converting to iron 2 and releasing 2 electrons will be our SRA, and that's minus 0.45 volts, isn't it? Yeah. But we're going from right to left. We're going from iron metal to iron ions, so flip that. We're going to get plus 0.45 volts from the way that reaction's happening in our cell. So positive 0.45. Sorry, I know I'm right against the edge there. Hope that's still readable. So, oxidation half reaction, careful. The SRA, the iron, is the one that's getting oxidized. This is an oxidation reaction because the oxidation state goes up. The silver is a reduction half reaction because its oxidation state is going down from +1 to 0. So those are the two reactions. The overall cell reaction is what we get when we add these together. So we just add those two half reactions, or do we? Is it okay to add these? Say no. If you said no, you're right. Why not? We can't add these because the electron counts don't match. This one's talking about taking 1 electron while this one's talking about releasing 2. Not good. We have to double this silver reaction. And remember, when you double an electrochemical reaction, you do not double its voltage. You don't get twice the volts when you use twice as much chemical in an electrocell. You get the same number of volts and a cell that lasts twice as long. So no change to that number. Now we can cancel our electrons, because there's 2 each, and we can mush these together into one big net reaction. 2 silver ions react with 1 iron metal. We get 2 silver metal and 1 iron ion, and 0.80 plus 0.45 makes 1.25 volts for the net cell potential. Good with all that? Okay. Next thing they get to, what happens to the masses of the electrodes? Over here we have a chunk of iron metal. What's going to happen to it as this reaction goes on? Well, according to this reaction, we're going to use iron metal, solid iron, and turn it into floaty dissolved iron ions. So over here, iron is going to dissolve and float away into the solution. That's going to eat away at this electrode. It's going to look like it's being dissolved in acid. It's going to look pitted at first. The surface will look a little dull, and then it'll actually start getting holes in it, and then it'll start to crumble and fall apart as it's eaten away bit by bit, and you get more and more ions in the solution. Iron ions have a bit of a color to them. It's greenish, if I remember correctly, for iron 2 ions. So you'll see more and more of that color in the solution as these ions pile up. On the other side, the silver, this reaction uses silver ions, which were floating around in the solution, and turns them into solid silver metal. So the silver ions in the solution are going to float up to the electrode and stick and turn into layer after layer of solid silver. This electrode is actually going to start to build up. It'll look like it's growing fur at first, because the ions tend to stick on in little filaments, and then it'll start to look clumpy as more and more silver piles onto it. When silver forms this way, it's not shiny, it's completely not polished, it's very rough on the surface, but you will still get more and more mass. This electrode will get fat as more silver deposits onto it. Silver ions don't have any color, so you won't see anything happening out in the solution, but you'll certainly see this electrode growing if you watch long enough. So silver mass up, iron mass down.